Alright, in this video we're going to first go over an important result on differentiating and integrating series term by term, and then we're going to apply the result to question 6 on the worksheet. Okay, so to start, let's suppose that f of x is equal to this series on the right, centered at a, and let's say this series converges to f of x for all x in some interval I. Okay, now I've drawn the interval I off to the right, and note that I've intentionally not indicated whether or not I have convergence at the endpoints. Okay, I'll say why I'm doing this in a moment, but for now we'll just leave it as is. Okay, so our first result says that we can differentiate this series for f of x term by term, and the resulting series converges to f prime of x on an interval with the same radius of convergence. Okay, and then I make a note here that says the convergence at the endpoints may be affected. Okay, so what does all of this say? Well, first off, what does it mean to differentiate a series term by term? Well, as the name suggests, it just means to differentiate each one of these terms on their own and then sum up the results. Okay, so the derivative of c0, well, c0 is constant, so its derivative is 0, and so you don't see a c0 down here. The derivative of c1 times x minus a, that's c1 times 1, and so that's just c1. The derivative of c2 times x minus a squared, so we use the power rule here, so this is 2 times c2 times x minus a to the first, and then note that the chain rule factor, which is the derivative of x minus a, is just 1 in this case, so we get 2c2 times x minus a. The derivative of c3 x minus a cubed, that's 3c3 times x minus a squared, and then we would have a 4c4 times x minus a cubed, so on and so forth. Okay, so now this resulting series converges to f prime of x on an interval with the same radius of convergence. Okay, so in other words, this resulting interval where this series here converges to f prime of x, okay, has the same center as the original interval, the same radius of convergence, okay, but the convergence at the endpoints may be affected. So let's say for the original interval we have convergence at the right endpoint. Well, it turns out that if you differentiate term by term, it's possible to lose convergence at the right endpoint. Okay, you could keep convergence, right? That also is a possibility. The big point here is that convergence at the endpoints, it may or may not change. You really have to just take things on a case-to-case basis. All right, great. So now for the next result, this is on integrating. So we can also integrate the series for f of x term by term, and the resulting series converges to the integral of f of x on an interval with the same radius of convergence. But just like we saw for differentiation, okay, convergence at the endpoints may be affected. So integrating this series for f of x term by term, okay, that's going to give us what? Well, integrating c0, that's c0x. Integrating c1 times x minus a, that's c1 over 2 times x minus a squared. Integrating c2 times x minus a squared, that's c2 over 3 times x minus a cubed. And then c3 over 4 x minus a to the fourth, and so on. And note that since this is an indefinite integral, okay, we also have this plus c, the constant of integration. Okay, so now let's go ahead and apply this result to question 6. And part A says, use the fact that the derivative of the natural log 1 plus x is equal to 1 over 1 plus x to derive the Maclaurin series for the function natural log of 1 plus x. And then it says, find an interval on which your series converges. All right, so the first step here is to recognize that this expression, 1 over 1 plus x, is of the form a over 1 minus r. Okay, so I can use our result on geometric series to expand this expression into a series. All right, so 1 over 1 plus x, well, that's 1 over 1 minus a negative x. So here I see that a is 1 and r is negative x. So expanding, right, I have the first term a is 1. Then to get to the next term, I'm going to multiply by the common ratio r, which is negative x. So that gives me a negative x here. Multiply again to get positive x squared. Multiply again to get negative x cubed, then positive x to the fourth, and so on. Okay, and here we have equality provided the common ratio r, which is negative x, is strictly less than 1 in absolute value. Okay, now note that the condition here that negative x in absolute value is strictly less than 1 is equivalent to just saying that x itself in absolute value is strictly less than 1. And so altogether here, we're saying that the derivative of the natural log of 1 plus x is equal to this series, 1 minus x plus x squared minus x cubed, and so on this interval where x is strictly less than 1 in absolute value. Okay, and I've drawn the interval off to the right. Okay, so that's all fine and good, right? But we ultimately want the Maclaurin series for the natural log of 1 plus x, not the derivative of the natural log. Okay, so I need to undo this derivative. How do I do that? Well, I do that by integrating. So our next step then is to integrate both sides, and on the left I'm going to get just the natural log of 1 plus x, and on the right, well, I'm going to integrate this series term by term. Okay, so let's go ahead and do that. So the integral of 1, that's x. The integral of negative x, that's negative x squared over 2. The integral of x squared, that's x cubed over 3. And then we have negative x to the fourth over 4, and so on. And then here I'm including this plus c, right, the constant of integration. All right, so now what about the interval of convergence? Well, as I noted in the statement of our main result, it's possible to have the convergence at the endpoints be affected. And in this case, it turns out that is the case. Okay, we now do have convergence at x equals 1. Now this, as I note here, is not an obvious fact. Okay, it's hard to prove. It goes beyond the scope of this class, but it is true that the natural log of 1 plus x does converge to this series when x is equal to 1. Okay, so here I've indicated the interval of convergence now for this series representation. All right, cool. So now what about this plus c? All right, well, we can evaluate the constant of integration by just plugging in a value for x. And to keep things simple, I'm just going to plug in 0 for x because a whole bunch of stuff drops out. Okay, if I plug in 0 for x, on the left I have just the natural log of 1. And on the right, all of these terms are just going to drop out, and I'm left with just a plus c. And now, noting that the natural log of 1 is 0, and on the right I just have c, that allows me to conclude that the constant of integration here is 0. Alright, so all together then, we conclude that the natural log of 1 plus x, which I write here, the series representation in sigma form, is as follows, right? We're summing negative 1 to the n plus 1, and here the index n starts at 1, and that's just giving me this sign alternation. Now the denominators are 1, 2, 3, 4, and so on, so I need an n down here. And then the powers of x, those are 1, 2, 3, 4, and so on, so I have an x to the n here, and there's just that same series in expanded form. And also note, now I don't write the plus c because up here I found that c was 0. Okay, now let's go ahead and before we press on to part B, I want to point out one thing that I mentioned back in, this was back in chapter 9. Okay, note when I plug in x equals 1, okay, what do I get? I get the natural log of 2 on the left, and on the right I get 1 minus a half plus a third minus a fourth, and so on. And we recognize this series as what we call the alternating harmonic series. Okay, and back in chapter 9 I'd mentioned that this alternating harmonic series does in fact converge to the natural log of 2, and it's a consequence of this series representation that we just derived. All right, cool. So now let's go ahead and turn to part B. So part B is having us do what? Well, it's having us find the first three non-zero terms in the Maclaurin series for the function 2x squared times the natural log of 1 plus 3x. All right, so now we can use this result that we just derived for the natural log of 1 plus x to help us out. Okay, the idea here is to replace x with 3x in this series representation for the natural log of 1 plus x. Okay, so we'll go ahead and do that here. So I have my 2x squared, and then it's multiplying this series representation for the natural log of 1 plus 3x, and note that in this expression that I'm summing, right, I've replaced x with 3x. So now I have 3x all to the n. Okay. Also, since I'm replacing x with 3x, I also have to make an adjustment for the interval of convergence. Okay, so here, instead of x being strictly greater than -1 and less than or equal to 1, I now have that 3x is strictly greater than -1 and less than or equal to 1. All right, now let's go ahead and clean this up a little bit. Okay, so here I'm going to distribute the 2x squared, so the 2 comes in right here. I still have the -1 to the n plus 1, that's right here. Now for the 3x to the n, I'm just breaking these apart. So I have my 3 to the n here, and then I have my x to the n here. And note that when I distribute x squared, that's going to bump up x to the n to x to the n plus 2. Okay, and then we still are dividing by n right here. And also note that taking this condition on x, right, if I divide through by 3, right, that's equivalent to saying that x is strictly greater than -1/3 and less than or equal to 1/3. All right, now the question asks for the first three non-zero terms of the Maclaurin series for this function. Okay, so what I'm going to do now is expand this out, and I'm going to get the first three non-zero terms. So when n is 1, well, I'll get 2 times -1 squared, so that's +1, times 3 to the first over 1 times x cubed. Altogether, that's 2 times 3 times x cubed, or in other words, 6x cubed. When n is 2, okay, I have 2 times -1 cubed, so that's a -1, times 3 squared over 2, so you see that coefficient right here, and then I have x to the 4th. Okay, and that simplifies to -9x to the 4th. Okay, when n is 3, we have 2 times -1 to the 4th, so that's a +1, times 3 cubed over 3, and then we have an x to the 5th. You see that right here, and this coefficient simplifies to an 18, so we get a plus 18x to the 5th, so on and so forth. Okay, and so here are the first three non-zero terms of the Maclaurin series for this function. All right, great. So that is going to do it for this video. In the next video, we'll look at a similar problem that's related to the arctangent function. All right, see you there.